Alright, sorry to leave you on a cliffhanger from the last video, but sections 5.1 and 5.2 really go hand in hand, and I didn't want to spoil any of the 5.2 stuff, but we are now ready to introduce the concept of integration. So, I want to start off by talking about our Riemann sum notation that we looked at in the last video. Again, what are we trying to do? We're trying to look at areas under curves. If we have some function, we want to know what is the area between the function and the curve. The way that we do this is through a process called Riemann approximation, where we create a bunch of these really, really small rectangles. Rectangles being something that's very simple to calculate the areas of. And yeah, some of these get upside down, which would imply a negative height. We'll talk about that when it comes to it. But the idea is we approximate the area under the curve, which is complex, with these Riemann sum rectangles, and rectangles being something very easy. So something that you're going to see notation-wise, I just want to point out to you. So all of these Riemann sum notations have the same idea. First of all, we use a capital S Greek sigma to represent a sum or an addition. And we're going to start at the first and end at the last. So that's what the below and the above say. And ultimately, these become a base times a height. Now, one way to do this is to start your index at 1 and go to n. And then you have your base is now just called delta x, change in x. And your height is the specific f of x sub I, where x sub I changes based on a left, a right hand, or a midpoint. Okay? So specifically, I want to jump to this new notation that uses K notation, and this is specifically a left hand Riemann sum. Where we once again have the base, and we have this x sub k, where there is an explicit formula for x sub k. Oh, sorry, I'm cutting off some of it. Now, the important thing to note is that x sub 0 is a. That's very, very important. And this should always be the case. Why? Because if it's a left-hand sum, it's always going to start with a. And then x sub 1 is a plus 1 base for whatever our base is, plus 1 delta x. So this index represents how many delta x, what I sometimes refer to as jumps, are we doing. And notice, because we're starting at 0, we're not going to go all the way to n. We're actually going to stop at n minus 1. One less than it. It's almost like we've re-indexed it. So let's take a look at an example in this. Okay, let f of x be the function e to the x, and we'll do the interval from 0 to the natural log of 7. And we want to use 25 subintervals. First step, we want to calculate what is our change in x, our delta x. We take b minus a and divide by how many there are. The natural log of 7 minus 0 divided by 25. We get ln of 27 divided by 25. Next, we're going to go out. We're going to write out all of our x sub k's. So notice x sub 0 is 0, which is a. X sub 1 is 0 plus 1 delta x, which is going to be the natural log of 7 over 25. X sub 2 is going to be 2 jumps from 0, 3 jumps 0, 4 jumps 0, 5 jumps 0. Notice that if we get to x sub 25, this would be 25 times the natural log of 7 over 25, which is natural log of 7, which is b. But please note, in a left-hand Riemann sum, this term is not included. It's really, really important that if you do a left-hand sum, B will not be included, and if you do a right-hand sum, turns out A is not included. But we almost exclusively use left-hand sums just for this notation. So now we're ready to write it out. The area is approximately equal to, oh, I'm sorry, I made a slight mistake here. Reminder, if we're using 25 subintervals, we're going to sum this from 0 to 24. It's just a counting notation. So we sum from 0 to 24 of delta x times f of x sub k, where we have a table to look up all of our x sub k's. And we know delta x is the natural log of 7 divided by 25. So here's our first term. Notice it uses k equals 0. Here's our second term, k equals 1, k equals 2, and here is the last term, k equals 24. And theoretically, if you were to add up all of these terms, all 25 of them, even though the index ends at 24, you get very, very close to the actual definition. Okay, so I want to take you to a Desmos screen just because I think this is interesting. We're going to do f of x equals e to the x. We can go ahead and take a look at it. I'm going to set up our x-axis from 0 to the natural log of 7. We'll go 0 essentially to 7. And let's make this just a little bit thicker just so that we can really, really see it. So this is the curve. We want to find the area underneath. And so we're going to make a sum. Now, I think I might be able to change this to k. We'll go from k equals 0 to 25. And so we need to write delta x, which I'll just call d. Remember, this was b minus a divided by n. Or, in other words, this was the natural log of 7 minus 0 divided by 25. So there was d. That's our base. And we're going to multiply that base by f of x sub k. But now we have to define what x sub k is. So let's say that x sub k is going to be 0 plus d times k. Now, if you take a look at this, what you're going to find is you just get an actual number. I'm going to take you to someone else's Desmos screen. I did not create this screen, but one of the nice things about Desmos being a very visual program is that there's all kinds of interactive Riemann sums that we can take a look at. So here's an example of one that, again, I did not create this. This is just available if you Google Desmos Riemann sum. And so you can see we have a function. I'm going to change this into e to the x. And you can kind of see our left-hand sum being built. Notice, we know it's a left-hand sum because all of these values intersect at the left side of the rectangle with the function. And we can go from a equals 0 all the way up to b is the natural log of 7. Number of intervals, let's choose 25. And so you can see, just visually speaking, this is an underestimation. And we know it's an underestimation because we can see all of this area that we're not including. But the idea is, if I increase the number of intervals all the way up to 100. Now I'm doing 100 things. Now, am I still underestimating? Yes. But in the grand scheme of things, how much underestimating am I doing? Let's go out 1,000. Let's go out 10,000. Notice this value right here, if you were to think about this as a limit, let's go from 1 to 10 to 100 to 1,000 to 10,000, all the way Notice this number doesn't change as much as you would think. So I'm going to go back to n equals 1. And I think I just broke it. That is one problem with these visual graphs is it's very easy to... it's trying to draw a lot of things. And I don't want to confuse it more than I have to maybe. So let's go natural log of 7. So we're going to start again. And here's what I want you to take a look at. Right here. This is our Riemann sum. Now they're using i's, but I use k's, but that doesn't really matter. It's a height times a base. Here's 1 Riemann sum. Here's 10 Riemann sum, or technically 10 subintervals of the Riemann sum. Goes to about 5.4. Here's 100, 5.9. Here's 1,000, 5.99. Here's 10,000, 5.99999. Here's 10,000, 5.9999999, on and on and on. It seems like, to me, I would believe that this is a limit, and it's limiting towards something close to 6 is going to be my guess. And so that's where we have to start making a leap. So remember that in the last section, when we talked about derivatives, we had this average rate of change, this discrete concept that was change in y or change in x. And we took a limit as delta x went to 0, and we turned the discrete a rock into the continuous I rock, the derivative, as we want to do the same thing with the Riemann sum. We take the discrete Riemann sum, and we turn it into the continuous integral. Now, it is technically the limit as delta x goes to 0, but turns out we don't like that. And this is kind of one of the reasons why Bernard Riemann is got named after this, is because really we're taking the limit as n goes to infinity. An infinite number of subintervals. And that infinite number of subintervals becomes an exact area. So, in our previous, we said the area under this curve was approximately equal to this. But here's what I can say. The area is going to equal exactly the integral from 0 to the natural log of 7 of e to the x dx. And I just have to figure out, what does this mean? And I need to point out, this is exact, and this is approximate. But the exact is the limit as n goes to infinity of the approximate. That's the idea. And that's really what Bernard Riemann was able to show with some rigor, is exactly how you do this. And we are eventually heading towards a very fundamental theorem in calculus. And you might ask, well, how do derivatives come into play? You'll be surprised.